Okay. Your time starts now.
Good morning, ladies and gentlemen. Good morning, members of the IB. Good morning, classmates. Good morning to my fellow teammates. My name is Fernando Pinheiro, and alongside with Brian DaCosta and Marco Betancourt, we are team number 1, the ShellEcoMarathon, for the 2013 Senior Design Project. So just a little table of contents, what we'll be speaking about today. First of all, introducing the competition and our project. Second, talking about the car design and the manufacturing following right after, and ending up with project management and a little clip about the event and how our experience went in Houston, Texas. So a little bit about ShellEcoMarathon. ShellEcoMarathon is a race, but a race a little bit out of the ordinary. It's actually a fuel efficiency race. So the team who wins is the team that who designs the vehicle that will run the furthest with the littlest amount of gas. You must maintain an average speed of 50 miles per hour throughout the competition and do 10 laps around a 0.6 mile course. Ending up with the winner, obviously, as I mentioned, the team who does it with the least amount of fuel. So on the next slide, a little bit about global learning in this competition. This competition is held throughout the whole world. There's 3 different stages. The one we attended in the Americas in Houston, Texas, one in Rotterdam in the Netherlands, and also one in Singapore. So teams from all over the world compete in the same competition under the same rules. We also had to research, adapt, and ideas and concepts from the diverse applications. There's also several different security rules that we must follow for this competition, such as putting arrows for our switch on and off of the engines to basically allow the staff of the competition to shut off the engine if anything bad happens. We need to learn and use new manufacturing techniques and also develop successfully multidisciplinary vehicle systems. So on the next slide, we'll talk a little bit about the FIU background. FIU has competed for the past 2 years in the battery category. So for the first time, we did compete in the internal combustion engine. It was a big challenge for us, starting a new car from scratch. We'll mention this a little later, but you see that most of the teams that are in the competition usually just build up from the cars they've had in the previous years. And this year we decided to do something new, to build one completely from scratch. So that was one of the biggest challenges for us, being the first team in the history of FIU to compete in the internal combustion category. So now we're going to the car design. First thing we're going to speak about is the steering system. Steering is usually not a major problem in the competition since the curves are very wide. According to our calculations, the wheels only had to turn about 15.8 degrees in order to clear the turning radius. So we went to, this is how we did the steering. We attached a carbon fiber tube to an aluminum tube that was welded into a C-clamp. The C-clamp was joined by these hubs, which were then connected, one hub to the other by a tie rod, and then we had a mechanism that would basically turn one of the wheels, and then the other one would automatically turn since they were both connected by one tie rod. So we had a little problem with this steering system since it was designed for a body that would stay outside of the wheels. Once we changed the body, we found out that there was not enough space for the steering to turn. So during the competition, we had to adapt. So on Friday night of the competition, we had to run to Home Depot. We bought some pulleys, bought some cables, and we created a whole brand new steering system. Very simple, 4 pulleys that would go around the driver, and once you move once you move the lever, basically the cables would pull and push and turn both of the wheels at the same time. It turned out to be very effective. Brakes and wheels, the whole key why our brakes and wheels were successful in this project was we used recumbent tricycle, the system. Our disc brakes turned out to be very effective, and so did the wheels, because the recumbent tricycles are very similar to the concept that we use in the competition. And now I'll pass it on to Brian, who will speak more about the body.
Good morning. As Fernando said, my role in the team was to build and design the body and the frame of the car. When we designed the body of the car, there was a lot of things that we needed to take into consideration. Like he said, the angle of turning of the wheels. We needed to take that into consideration so that the wheels would not hit the frame of the body once it was turning. And initially, we wanted it to be the wheels inside of the body. But later on, I will go into more details and show how that actually affected us in a way that we were forced to basically put the wheels outside of the body. Here are the initial 3 designs. We went through a lot of designs for the body. We drew at least 5 different ones. These were just the initial ones. We wanted to play around to see how the tail of the body would affect the results of the drag, how the inside, how the position of the tires would affect if it was underneath, if they still protruded outside of the top of the car. This was our, I guess you could say, the second stage of the design process. We expected the car to look something like this. Like I said, we wanted the wheels to be on the inside of the body. We felt that that's the most efficient way for the aerodynamics of the car. But unfortunately, we had to change it. This was our final design. Here, the car, it looks like this because only the back wheel is inside of the body in this case. The two wheels would stand, would be right here in front of the car, and they would be actually on the outside of the car. The final design, the dimensions were, it was 29 inches tall, the height. It was 27 inches in width, and 101 inches in length. It was close to 9 feet. The driver compartment, which is something that I want to specify, is it was only 54 inches long. So we actually had to get a driver that was either 5 feet or shorter to drive our car. And yeah, we made it possible. Now I'm going to let Marco talk to you about the engine.
My name is Marco Betancourt. I am the powertrain and energy delivery engineer for the project. And I was responsible for sourcing the engine, getting it working, and building all the auxiliary systems that control the engine. So we started choosing the engine by plotting the power requirements that we expected for the vehicle to need during the competition based on the vehicle weight, the expected drag, and the inclination of the track relative to gravity. So because that was actually one of the largest components of drag. The engine that we chose was a GY6 scooter engine. It comes right off any scooter, almost any scooter in the world. And we chose this package because it integrates a lot of the systems that we needed to source and apply on the vehicle. It had integrated brakes, suspension, and an electric starter. It brought its own transmission, and it came ready so we could just mount a wheel on it and get it running. It also had the highest compression ratio among all the other engines in its class, and as you know, this increases our thermodynamic efficiency. Besides that, we chose it because it's also a very popular engine, and there are lots of parts, of aftermarket parts, that are available to increase its performance. And the only drawbacks of choosing this power plant was that it was relatively heavy compared to the other options, and it had a high rolling resistance compared to other systems that we would have to design. But this is what we went through, and we continued by trying to improve on the worst aspect of the engine, which was the transmission. A CVT transmission gives us a very wide range of gear ratios that we can, that our vehicle will use, and therefore it can traverse different types of driving conditions. But on the other hand, it's also one of the most inefficient types of transmissions. And we started including different upgrades to make it more efficient. We made it engage at a lower RPM speed. We improved some parts that made friction inside the clutch, and we used a better belt that would reduce the amount of friction created in the transmission. Can you continue, please? Further on, we had to develop the electrical system to get the engine running. This was a very difficult and involved process because we had to design we had to learn how the engines are wired, how all the components come together and start connecting everything. And we had to put fuses and protection in almost all the connections to avoid burnouts and shorts. but this is our electrical system, and it worked. So we moved on to design the fuel delivery system. Our fuel delivery system had to be pre-pressurized. So we had a bottle of air, like a plastic bottle that we pressurized with 70 psi of air, and with that we were able to pressurize, to regulate it down to a pressure that would be acceptable for the injector to function. We had to develop this because we had to develop a fuel injection system for the engine in order to save more gas and make it more fuel efficient, versus a carbureted option, which the engine already came built in with. But we wanted to do something better. So this is how the engine looked with the whole fuel injection system and the fuel delivery system connected. Everything in the table was the fuel injection components and the ECU. And the ECU, then we had to tune it and make it learn how the engine would work and how much fuel it had to input at any given time at any given engine load. We used a wideband O2 sensor to help us fine-tune this even more than the stock ECU would allow. And we did notice that there was a limitation of the ECU, which would just engage closed loop analysis after 3 minutes of engine running time. So we had to be very careful in tuning the tables before the computer actually kicked in and started calculating how much fuel they had to inject on its own. For the tire selections, we went with low rolling resistance tires for the front, and in the rear we got the lowest possible rolling resistance tires designed for scooters, which will also just be a direct fit on the engine.
Right, now to start talking about the actual manufacturing of the body and the frame. I'm going to start off with the frame. So what we did is we actually used a very innovative method to create the frame. We wanted to make it as light as possible, and in order to do that and still maintain the integrity and the strength of the structure, we decided to go with carbon fiber. The entire frame was actually made out of carbon fiber, even the junctions where all the tubes connected. To go into more detail specifically about how that procedure worked, we got carbon fiber tow, as you can see in the picture on the left, and we actually wrapped carbon fiber tow around some mandrels, and then we applied resin. Once it dried off, it actually took a very strong and concrete shape structure, and here in the right picture you can see what we did is we took those mandrels and we cut them by half, and then they became basically U-joints. Once we had those U-joints solidified, what we did is that we reinforced the tips, the loops of those U-joints even further, just to increase the integrity of those parts. After we did that, what we did is we actually went on to wrap those U-joints around the tubing, the carbon fiber tubing, as you can see in the pictures. We reinforced it even more, wrapping it around, applied even more resin. By the end of it all, the structure was really sound. As you can see in the next slide, this was the final product of the frame. You can see that all the joints were tied furthermore with even more carbon fiber tow. We were very pleased with the end result of the frame. We were skeptical at first because we had never actually seen that method, but we were very pleased because it withstood a lot of force, and it was very, very light. It was, the whole thing altogether was under 15 pounds. Now to start talking about the body, the way that we manufactured the body is that we started with some hot wire foam cutting. This is basically the blueprint that we used in order to start the process. What we did is we sent it to a manufacturer, and they cut cross sections out of foam using the hot wire method. In this picture, what they did is they took those cross sections, and every 2 cross sections became 1 piece of foam. So once you put all of them together, as you can see in this picture, they start taking the entire shape, and this is basically the final product. Although we were very happy with the way that it looks, I'm not sure I would recommend this method because it allows for a lot of error. A lot of human error, especially when you're doing the sanding. After we did the manufacturing of the foam, we applied a coat of resin, and then we applied another coat of filler in order to fill in the gaps that we created when we were sanding down the foam. Next one, please. Basically, after we did that, after we filled it all in, we just applied the fiberglass onto it, and we further did more sanding, and then we applied a layer of paint to it. And this is basically the end product of our body.
All right, I'm going to try to speak a little bit about project management.
Finish it up.
Just keep going. I mean, if you go over time, we wanted to know how much you went over time so you can adjust for the
Adjust,
final.
yeah.
Okay, I'll try to be as brief as possible. As you can see, we met the project timeline since we got the car ready for the competition. We actually had the car ready a week before, so we were able to ship, not a week, but I would say 4 or 5 days before the competition, so we were able to ship the car and get everything on time. If we had to change anything as far as project management, it would actually be nice to have maybe 1 or 2 extra days before shipping the car so the drivers could have some practice. So I would say that we were on point as far as the project management, but maybe missed by 1 or 2 days for the driver to have some practice. On the next slide, you see our expected cost analysis very briefly. We thought the project would cost about $7,500, and we expected to pay out of pocket something like $2,400. And on the next slide, you see that the total cost of the project almost came out to $10,000. But fortunately, since Shell gives you $1,000 to go up to the competition for travel, and we're able to get some funding from our Student Government Association for the flights, even though the cost of the project was $10,000, we ended up spending less than we expected out of pocket, only $1,914. And so we went to Houston and we presented a little, this is the single vehicle frame, vehicle race, and then press play on the video.
There's a play button.
QuickTime is not available on this.
Just one thing.
Okay.
It doesn't have QuickTime, so you might have to look for something.
We'll
Windows
prepare the video for
Windows Media Player.
How long is the video?
2 minutes.
Yeah.
Okay, well, you're 16 already, so you got to start working on some adjustments.
Yeah, absolutely.
All right? All right, so so you're done.
Yeah,
All
after the
right,
video.
so that's 17 minutes?
Yes.
All right, so you got to shave 2 minutes, and then you got to allow 2 minutes for your video.
Okay.
So you got some work to do. All right, I got a few questions that will help you get things cleaned up for the IAB. For the global learning initiatives, it would be a good idea for you to make reference to both SI and USA units in your comment.
Okay.
Because then you're addressing global issues, because you have no reference to units. And of course, when your car is going to be competing over in Europe, you're dealing with SI.
Okay.
And the fuel is not miles per gallon, fuel consumption is not miles per gallon anymore, okay?
Right.
It's liters per kilometers or whatever. Okay, all right. The design analysis, it looks like you had to tweak some things with trial and error. Did some of those issues not manifest themselves during the analysis, or what kind of analysis did you do that would not have allowed you to see some of those issues with the turning radius and all of that?
I guess the major issue is just we didn't want to have a car that was too fat. That was basically, we didn't want to have a car that was going to be too wide. We